Before I proceed with the video, I have one thing to say here. I am amazed by your reactions to the movies. You subscribe, ask in the comments, and this is great because the more communication there is between us, the more interesting this cooperation becomes. I'm also impressed that no one complains that these shaders are hard or complicated or something. Thanks again, and let's go. In the course of this video, I will show some basic transformations on UVs that can be performed inside the shader. Later, we will combine these methods to create automatic UV mapping, called planar mapping. So, UV coordinates of polygons' vertices describe which part of the texture should the polygon use. Each vertex has its own coordinates on a texture that doesn't change even when the model is being deformed. It's a stable projection. And the texture always fills the entire space between 0 and 1 on each axis. Left bottom corner is 0, 0, while the right top corner is 1, 1. Together, U and V coordinates form a vector, a two-element value. Keeping them as vectors allows us to perform math operations more easily. The UV space is often visualized as gradients of red and green. So we will need some basic operations on vectors to be able to transform our UV space. Translation is done by adding an offset to the original UV position. Scaling is multiplication. You multiply the position by a given number. In shading languages, math is performed per component, which means that x is multiplied by x and y is multiplied by another y, and together they form a vector again. Every texture repeats infinitely by default, so exceeding the 0-1 bounds gives us repetition, also called UV tiling. By adding the current time to position, you can get animated UVs, for example in a river or in a moving neon sign. If the UVs can be transformed, they can be obviously generated as well, because they are just numbers. And this allows us to create our planar mapping. Globals position x and y multiplied by a scale become our u and v on a texture. An offset can be added, so we have more control over the final mapping. So do you remember that UV mapping is projecting a 3D model into 2D space? It's not as easy as it seems. Take a sphere for example. We have 3 different mappings, and this is only the beginning of ways to map a sphere. A typical 3D editing software usually offers multiple algorithms to unwrap our models into UVs. Every such projection has a goal of minimizing stretches, but in organic models that are not axis aligned, you can't really avoid them. So remember to use the planar mapping only for flat or almost flat surfaces, because otherwise, for higher angles, it will definitely lead to bad looking stretches. Making it in Unreal Engine goes like that. Press and hold the U key on the keyboard and click. This creates a node which gives us original UV coordinates. Then hold A and click to create an add node. Then either S for a scalar parameter or V for a vector. An append node will join scalars or vectors to form a bigger vector. You should always operate on vectors of the same size, otherwise you will get a cast error. Animation is most simply done in Unreal Engine with a panner node. If you want manual control instead, you can use a time node. Multiply it by desired speed, then add to UVs. An important improvement is to place a frac node in between, so it returns only the fractional part of a number. Without it, values could become extremely big over time, which is bad because floating point numbers have limited precision. Creating the planar mapping requires us to take the word position node and the other vector operations we know. Sometimes it can be useful to pack all the parameters, which is scale x, scale y, offset x and offset y, into a single 4-element vector, just for convenience, so we don't use separate 4 parameters. And it works like that. After you master this introductory material, there are many more things that you can do with UVs in the shader, definitely worth checking out in the future. For example, flow maps, which is modifying UVs per pixel with a texture. It makes the motion more varied. Translation by discrete steps, also dubbed by Epic as sub-UVs. The rotator node to rotate UVs. And polar coordinates. So instead of using the Cartesian XY, you can use polar coordinates for angle-based deformations. If you have some questions, especially about the last slide in which I only mention things to learn in the future, feel free to ask in the comments, and see you next time.